The topic of this session is increasing and decreasing functions. Let us see the definition. Increasing and decreasing function. We say a function f from I to r is increasing on interval I if whenever x1 and x2 in I, these are the 2 points, satisfy x1 is less than x2, then fx1 is less than or equal to fx2. That is, the value of function f at x1 is less than or equal to value of function at x2. Similarly, we say f is decreasing on interval I if whenever we are having 2 points x1, x2 in I satisfy x1 is less than x2, then fx1 is greater than or equal to fx2. That is, the value of function at x1 is greater than or equal to value of function at x2. We also say f is decreasing on I if the function minus f is increasing on I. For example, fx is equal to x square is increasing in close interval 0, 1 and decreasing in close interval -1 to 0. Because let x1, x2 are 2 points in close interval 0, 1 with x1 is less than x2, then we have fx1, that is x1 square, is less than x2 square, which is the value of function at x2. That is, whenever we are having x1, we have x1 is less than x2, the value of function at x1 is less than the value of function at x2. So function is increasing in close interval 0, 1. Now let us take 2 points x1, x2 in close interval -1 to 0 with x1 is less than x2. Then fx1, that is the value of function at x1, which is x1 square, is greater than x2 square, which is the value of function at x2. So x1 is less than x2, but the value of function x1 is greater than value of function at x2. So this function f is decreasing in interval -1 to 0. From the graph, it is clear. You can see this is the graph here. From -1 to 0, it is decreasing, and from 0 to 1, it is increasing. Now let us see a theorem. Let f is a function from I to r be differentiable on the interval I. Then first, f is increasing on I if and only if f dash x is greater than or equal to 0 for all x belongs to I. And f is decreasing on I if and only if f dash x is less than or equal to 0 for all x belongs to I. That is, f is increasing on I if and only if the derivative of f at any point x is greater than or equal to 0 for all x belongs to I, and it is decreasing on I if and only if the derivative of f at x at any point x belongs to I is less than 0. Let us see the proof. Suppose that f dash x is greater than or equal to 0 for all x belongs to I. If x1, x2 in I satisfies x1 is less than x2, then we apply the mean value theorem to f on the closed interval I, x1 to x2 to obtain a point C in open interval x1, x2 such that is we are applying mean value theorem on closed interval x1, x2 such that fx2 minus fx1 is equal to f dash c into x2 minus x1. This is according to Lagrange's mean value theorem. Since f dash c is greater than or equal to 0 and x2 minus x1 is greater than 0, so this side is greater than 0. So it follows that fx2 minus fx1 is greater than or equal to 0. Hence, fx2 is greater than fx1, and since x1 is less than x2 are arbitrary points in I, we conclude that f is increasing on I. Because x1 is less than x2, we have got fx1 is less than fx2. So f is increasing on I. Conversely, suppose that f is differentiable and increasing on I. Thus, for any point x which is not equal to c in I, we have fx minus fc divided by x minus c is greater than or equal to 0. Either x is greater than c or x is less than c. Still, in both cases, this expression is greater than or equal to 0. As we conclude that f dash c, which is equal to limit x tends to c, fx minus fc upon x minus c is greater than or equal to 0. Now c is any arbitrary point we have taken. So we can conclude that f dash x is greater than or equal to 0 for all x in I. Now let us see this example. Example number 1. For function fx is equal to x square minus 3x plus 5 from R to R, find points of relative extrema, the intervals on which the function is increasing and those on which it is decreasing. Solution. We have f dash x is equal to 2x minus 3. That is finding the derivative of this function. Now equating this derivative to 0, we got x is equal to 3 by 2, or so x is equal to 3 by 2 is point of extrema for the function fx. You can see this is the point. Now this divide into whole real line into two parts. So in interval minus infinity to 3 by 2 from this to this. If x belongs to minus infinity to 3 by 2, then x is less than 3 by 2, which gives 2x minus 3 is less than 0. So that derivative of f at x in this interval, that is 2x minus 3, is less than 0. So fx is decreasing in the interval minus infinity to 3 by 2. Now let us take interval 3 by 2 to infinity. In this interval, if x belongs to 3 by 2 to infinity, then x is greater than 3 by 2, which gives 2x minus 3 is greater than 0. So that f dash x, that is 2x minus 3, is greater than 0. So fx is increasing in the interval 3 by 2 to infinity. Now let us take this second example. Our function gx is equal to x upon x square plus 1, x belongs to R. Find points of relative extrema, the intervals on which the function is increasing and those on which it is decreasing. Let us see the solution. We have g dash x, that is derivative of this function, is x square plus 1 into 1 minus x into 2x divided by x square plus 1's whole square, which on solving gives 1 minus x square upon x square plus 1's whole square. Now equating this derivative to 0, that is g dash x is equal to 0, implies 1 minus x square is equal to 0. So that x is equal to plus minus 1 are points of extrema for the function gx. Let us see. Now this divides into real number line into three parts: minus infinity to minus 1, minus 1 to 1, and 1 to infinity. Now in interval minus infinity to minus 1, if x belongs to minus infinity to minus 1, then x is less than minus 1. This implies x plus 1 is less than 0 and x minus 1 is also less than 0, which gives 1 minus x square, that is 1 minus x into 1 plus x, is greater than 0. So that g dash x, which is 1 minus x square upon x square plus 1's whole square, is greater than 0. So gx is increasing in the interval minus infinity to 1. Now let us take interval minus 1 to 1. If x belongs to open interval minus 1 to 1, then minus 1 is less than x less than 1. This implies x plus 1 is greater than 0 and x minus 1 is less than 0, which gives 1 minus x square, which is 1 minus x into 1 plus x, is less than 0, because one expression is greater than 0 and this is less than 0. So that g dash x, which is equal to 1 minus x square upon x square plus 1's whole square, is less than 0. So gx is decreasing in the interval minus 1 to 1. Now finally, the interval 1 to infinity. If x belongs to open interval 1 to infinity, then x is greater than 1. This implies x plus 1 is greater than 0 and x minus 1 is also greater than 0, which gives 1 minus x squared, which is product of 1 minus x into 1 plus x is greater than 0, so that g dash x is greater than 0. So gx is increasing in this interval. Thank you.